our main part here is going to be reminding ourselves, am I looking for straight line velocity? How fast am I going if I stretch it out? Or am I looking for what's the angle measure spinning round and round as I'm looking at this? So, we're going to try and simplify this a little bit right off the bat. Linear velocity has to do with distance traveled, feet, miles, kilometers, per time, per second, per hour, per minute, etc. Seeing the labels that are involved are going to help us be able to figure out if we're going in the right direction or not. If we want to know the amount of distance traveled over a time in a circular motion, so it's still circular, such as how far a tire is rolled, again, how fast is it happening, distance per time is linear. So sort of just like I said, thinking if we took that tire and we just kind of stretched out how far it was going. So, the linear velocity, v, we're going to want to start learning these symbols too, because half the battle is figuring out, now what is that again? Of a point moving a distance, s. You're like, wait, s, haven't we used that already? Isn't that arc length? It's the same idea. If you think about it, that would be a distance as well. On the circumference of a circle in some amount of time given by this formula. All the formulas we are using today are on your help sheet. Okay? More on that in a little bit. So, linear velocity equals distance over time. Find the linear velocity of a bug, U, stuck on a tire for 5 minutes if the bicycle wheel traveled 2 miles. Okay. So here, my distance is 2 miles. My time is 5 minutes. So you're like, okay, let's see. And since we're doing applications, yes, most of the time decimals are going to be fine and actually preferred. So here we'd have 0.4 or 0.4 of a mile per minute. And labels are huge. Great if we get the number. Got to have the label. But again, you're just kind of labeling the parts as you go. So you're like, why are you saying this is bad? This ain't bad. And it's not overall. Again, especially if you're just given the distance and the time. So we won't go too crazy with these. So distance, 3 feet. Time, 2 minutes. Pop that in the calculator if I need it. 1.5 feet per minute. But I'll make note of something here. Remember, when you're doing v, linear velocity, distance over time. Okay? That's kind of your clue. When you get to an answer, that's kind of telling you if you're using the right formula or not. You're going to see that as we start to change it up a little bit. But as long as, again, you've got the formula right in front of you, if you've got the pieces, we just kind of plug and go. But am I always going to be nice and come straight forward? No, you know me better than that. Find the distance, s, covered, s, oh, I guess I could have just underlined it there, by a point moving with the linear velocity v for a time. It's the same formula, but now I'm looking for s. Now, this is just me. I'm more of a fan, since now the magic value is s instead of v, I'm going to go ahead and I'm going to solve this equation for s. So to do that, I'd multiply both sides by t. So distance would equal linear velocity times time. Now, could I just plug the numbers in like this and do the algebra? I could. If you like to do one-stop shopping, maybe that's better for you. But for what we're doing, we're going to look, we're going to go, okay, so if I've made this adjustment, my distance is going to be 45 miles per hour times 1/2 hour. Or you could say 0.5 hours over 1 if you wanted to go to decimals, you could. But the reason I want you to see this is, if we set it up right, the times will cancel, because what am I looking for? I'm looking for a distance. That doesn't have anything to do with time. And so I'd have 45 miles over 2 and divide that out. I get 22.5 miles. Now, even with these, there can be a twist now and then. So here comes the twist. You're like, well, this is, okay, V and T still, this is cool. We're kind of going along. We're like, all right, 63 miles per hour. Be careful. You need the same measure, whether it's your distance or whether it's your time. Hours and minutes are not the same thing. So, typically, if your velocity, your linear velocity, is in hours, we're going to put this into hours. So, you have a couple of ways you could do that. You could do, this is a little dangerous, but we could do it. Now I want to make sure I'm doing this right before I get going. Yep. How many minutes are there in an hour? 60. Now, right, you have two ways, and I'm going to show them both here because everybody thinks a little bit differently. Some of you are like, okay, Hardy, you're making this harder than you need to. I mean, I can multiply 63 times 10 and then divide it by 60. 10.5 miles, because again, it's a distance. Some of you are going to say, why wouldn't you just, and this is actually the way I normally would do it. I look at that and I say, hey, 10 minutes is how much of an hour? Well, if 10 minutes out of 60 is 1/6, you could just do 1/6 of an hour, cancel out the hours, and end up in the same place. Okay? If you don't like doing it stretched out, going from one measurement to the next, doing dimensional analysis like you did in Algebra 1, that's fine. I mean, it doesn't matter. It just depends on how you're going to work it through in your head, but they both get to the same spot. So it's usually not too bad. You're like, okay, got to make a little adjustment now and then. Cool. Might have to change the equation, might have to change a measurement. Not terrible. So see, it's not bad, it's just getting used to. Okay. Angular velocity. Angular, as it says right in the word, how much the angle sweeps out and moves over time. So again, it depends on what we're looking for. So angular velocity is measured in radians per unit of time. Radians per minute, radians per second, radians per hour. It's not something necessarily that's measurable, it's a label. So when I say that, okay, we're going to start using some different verbiage here again. We're not using theta anymore. Now we're going to use omega, this fancy looking W shape, where the angle must be measured in radians. Okay, so what does that mean? Another formula. Great. Angular velocity is my angle measure divided by time. Find the angular velocity. Okay. I'm just plugging straight in. Yep. So let's see here. Angular velocity is my angle. I hate vertical dividing, so I'm not going to do it. So I'm dividing by t, but we know what that really means. We're multiplying by the reciprocal. And sometimes you'll be asked for exact values. Sometimes it'll say decimals. I typically go back to exact values unless I'm asked to do otherwise. So, Hardy, though, what's my label going to be on this? Radians are always part of my angular velocity here. And I should have been a good boy and been putting this on here as I went, so it would be easier to see. So 2 pi over 15 radians per second. Like, it's a weird large label, but that's how we can tell the difference between angular versus linear, where it's inches, miles, feet, whatever that happens to be. Here's the other kicker. We're also used to, when we talk in radian mode, radian, we always have pi involved in it. If you're given a number and you don't see a degree measure there, that is already in radians. Now, if that would have said 24 degrees, then we have to make a conversion because it has to be in radians. So this is already in degrees. They're already in degrees. Oh, Hardy. Radians. I was thinking ahead. Unless there is a degree notation. So, if it's degrees, I convert. If it's just a number, I don't. I'm just going to leave what's there for me, which is going to make my life a little bit easier anyway. So all I've got to do here, if that's true, is go angular velocity. Again, it's still in radian, and I need that label. Because otherwise I just have 4 per minute. You're like, 4 what per minute? 4 radians, okay? I don't have inches or feet or something like that to use anyway. So that kind of helps me realize that I'm on the right track too. So labels are going to be super duper important. Okay, here's the one point where we might have to take a deep breath. A point P moves with angular velocity, omega, on a circle of radius r. Woo! Find the distance traveled by the point in time t. You're like, okay, wait a minute. So you're looking, you're like, I got angular velocity, I got radius, I got time. So here's where we're going to pull our help sheet back up. And at first we're going to think this isn't very helpful at all, but we will find that it is. So you're looking up here for a formula that has all of these in it. And you're like, well, wait a minute, though. So I see omega and r for, linear velocity, but I don't see a t. Then I go looking around, and I'm like, well, if I get here I've got omega and t, but I don't have theta. What the heck? We're going to have to convert a couple of these equations. We're going to solve them for the same variable so we can make us one new equation out of this. So I'm going to write the steps. Just stay with me. Okay? And I'm going to kind of let you see here what's going on too. All right. Formula number 1 to play with. Theta equals angular velocity times time. Okay, Hardy, where'd that come from? Here, if I take this equation and I solve it for theta, I'll explain while I'm doing that in a minute, I'd multiply both sides by t. So theta would equal angular velocity times time. That's the first piece of the puzzle. You're not going to have to do this whole thing every time. I'm just letting you see what I'm going to do is where it's coming from. Okay. Formula 2. This is the one we've already been playing with. Okay, your arc length, your distance, is the radius times theta. So, if I solve that for theta, we're going to divide both sides by r. So theta is my distance divided by radius. Okay? We're almost there. So, if that's true, then if theta is angular velocity times time, but theta is also the distance divided by the radius, it would be true that angular velocity times time must equal the distance divided by the radius. And if I'm looking for the distance, if I want to solve for s, I'm just going to multiply both sides by r. Over here, the r goes away. I just have s. Over here, I got r times theta times time. This is how now I have all three pieces. So notice again, that is nowhere on here. It's going to be pieces. Out of everything I say today, that is the one formula you are going to have in your brain. Otherwise, you're going to have to create it like I did here in the middle of a test, and I don't think you're going to want to do that. So just keep that in mind if you're asked to find the distance traveled. Whew! Okay. But once I have that, this isn't going to be bad at all. So, we've got 2 radians per second times 4 inches. We'll just put that over 1. Times 5 seconds. And we're going to have our first little discussion point. So I look and I go, okay, the seconds cancel. 2 times 4 times 5 is 40 inches. Hardy. You're about to say you went bonehead again. Hardy, you didn't put radians. You're right, and I meant not to. Wait a minute, the radians didn't cancel. Why did they just disappear? Remember, radian is a measure of an angular value. This is not an angular value. This is a distance. So this is where that label need not apply. Okay? I wouldn't say 40 radians per inch. Radian is not a measurement of distance this way. So that's the one part with this that gets tricky. It's the one time we ignore our dimension analysis is when we're dealing with, a straight distance like this as I fall on my face. Yeah. So, as long as I can get around that, we're going to be okay. And so, just to make sure again, because this is going to happen a little more often than we would like. So I get here, and I'm like, okay, 15 radians per second, 5 feet, be careful. Like, oh crap, Hardy, why do we got to be careful? Seconds and minutes. Make sure, okay, that you don't just go so fast that you'd see it here in a minute anyway. I need the seconds to go bye-bye. So since there's 60 seconds in a minute, okay, we're gonna have another discussion here in a minute. We'll get to it. This is the mathematicians going against their own logic and reasoning. It happens. Oh, I can't do that in my head. 15 times 5 times 6. Oops, 15 times 5 times 60. 4,500 feet. I'm just looking at one thing. Yes, okay. The fact that it's the minute doesn't matter because, again, it's the distance. I'm having to, remove all logic, which is terrible for a mathematician to say. but I do on this because my radians don't get to play around. They don't like it either, and my feet don't get to, my minutes don't get to either. But that's just what we have to do sometimes, which is the craziest thing ever when we're looking at this. I'm going to cut one thing off here. So, after that craziness, which I almost want to tell you to put out of your head for the moment, we're going to do one last thing. I'm going to wrap with an easy thing. We're going to do this little bottom portion tomorrow when we're going to have more playtime. Even though we're going to have plenty of playtime today, more than I thought we were going to have. Okay, units. Anything that is measured in theta, okay, which again is angular. So we're talking radians. If you have a degree measure, we talked about that on the front, you've got to multiply by pi over 180 to get rid of the degrees and get it to radians. Okay? So for instance, I'm going to kind of split these off. That's what they were supposed to be. So, how many radians are in 5 revolutions? Every revolution, how many degrees are there in a revolution? Full circle is 360. Or if we speak radian, 2 pi. So, if it was asking us how many radians are in 5 revolutions, since we're always speaking in radian, five revolutions would be 10 pi radians, because every revolution is 360 degrees, or 2 pi. So, kind of connecting the dots here, even though it's 360 degrees, we don't like degrees. We don't speak degree when we're in radian. We speak pi. And again, that's not the distance around your circle, because we'd have to know unless the radius was 1. If the radius is bigger, I have to plug it into the formula. This will help me start to get there, but it's not the only answer. Because the larger my circle is, the larger a distance angularly that I'm going to be moving. So here's all you have to remember from all this. If you're given something in revolutions per minute, and you're asked to find the angular velocity, all you have to do is multiply it by 2 pi. 40 pi radians, and these are always going to be in minutes. So no matter what the RPM is, decimal, huge number, little number, you're just multiplying by 2 pi. And going to radians per minute. Okay. I'm going to save that last little chunk for tomorrow because I don't want you to go into 0 time to do anything today. That'd be kind of dumb on my part. So, we need a little taste of this today. We don't have to go crazy. So, for the time being, on pages 3 and 4 in your packet, we are looking at odds or evens. As usual, odds are right there in the packet. Evens, I've shown my work online or up here in the front. The likelihood that you're going to be asked to do the opposite of what you did today tomorrow is very high. Very high. Because we need to make sure that we get the practice in on this to be good at it.